Hello everyone. Today we have section 11.4 from the Briggs textbook. This is the final section that we will talk about in chapter 11. The next chapter that we talk about is chapter 12 and deals with a very different concept than what we've been studying so far. But chapter 11 is kind of the culmination of the idea of working with Taylor series. And so now we start to get into the idea of different things that we can do with these Taylor series that we have come up with in section 11.3. All right, so let's get going. First of all, let me just remind you of all of these common Maclaurin series. So on an exam, you guys would be given this information if you were asked to use it. So for example, we might give you the fact that e to the x is equal to 1 plus x squared over 2 plus blah blah blah, xk over k factorial. It's equal to this infinite sum. We would give you that information and ask you to do something with it. Or we might give you the one for sine of x or cosine of x or whatever. Alright, so with that information, we can actually use these Taylor series to creatively solve some problems. So the first thing that we're going to discuss is the idea of solving a limit using a Taylor series. So suppose that we want to solve the limit as x approaches a of the function f of x. If f of x contains another function, g of x, which has a known Taylor series expansion around a, so specifically around this number here, then we can replace g of x with its Taylor series expansion around a. So for example, if f of x was something like f of x equals g of x plus 2, then we would replace g of x with its Taylor series expansion. All right. We also note that if the limit is approaching infinity, we technically don't have the tools to replace a function with its Taylor series centered at infinity. So to resolve this, one potential strategy we could do is write that the limit as x approaches infinity of f of x is equal to the limit as t approaches 0 from the right of 1 over t. So basically, every time you see an x, you would replace that with 1 over t. And instead of taking the limit as x approaches infinity, you now take the limit as t approaches 0 from the right. Okay, that shouldn't be too common of a strategy that we end up using, just a note for you guys to have. So let's do an example. Suppose that we're trying to evaluate the limit as x approaches 0 of x squared plus 2x, x squared plus 2 cosine of x minus 2 all over 3x to the fourth. Alright, so one thing that we know is that cosine of x has a Taylor series expansion around 0. Specifically, it has a Maclaurin series. Remember that a Taylor series expansion around 0 is just the same thing as a Maclaurin series. So let's write that the Taylor series expansion for cosine of x around x equals 0 is, and it is specifically the sum from k equals 0 to infinity of negative 1 to the k power times 2x, sorry, that's not right, times x to the 2k power divided by 2k factorial. That is the Taylor series expansion for cosine of x. Specifically, we know that this thing is equal to cosine of x because in the last section we showed that the remainder approaches 0 as n gets closer and closer to infinity. Alright, so anyway, the idea is that we will use this substitution. We are going to replace cosine of x with this infinite sum. And that will give us some idea on how to compute this limit. So first of all, let's actually take a look at this limit before we start doing any formal calculation and ask ourselves why we would care to do this in the first place. So first of all, if you were to just straight up plug in 0, then what you would end up getting is 0 from this x squared plus 2 from the 2 times cosine of x minus 2 from this guy. And then on the bottom, you would just get 0. So this is a 0 over 0 indeterminate form. So one thing you could do to resolve this limit normally, if you weren't thinking in terms of Taylor series expansion, would be to use L'Hopital's rule. And certainly you could do that. That would work. I believe that at the end of this, you would have to end up doing this 4 times to make it work out properly. I could be wrong. You might have to do it fewer times. So L'Hopital's rule would work, but we're going to just show you that this alternative method of using a Taylor series expansion works as well. So let's take a look. We're going to rewrite this limit, replacing cosine of x with its Taylor series expansion. This thing that I'm writing down is exactly equal to cosine of x. And then we divide this entire thing by 3x to the 4th. Alright, so why in the world would we do this? Let's take a look at what happens whenever we start writing the terms of this Taylor series expansion. So if we start doing that, this is going to be equal to the limit as x approaches 0 of, on top we have x squared plus 2 times. So actually I'm going to write that minus 2 over on the left here just so it's a little bit clearer. So 2 times. So the first term of the Taylor series expansion is 1. The next term is minus x squared over 2 factorial. After that, it's plus x to the 4th over 4 factorial. And then minus x to the 6th over 6 factorial. And this continues, right? This continues on forever. On the bottom, we have 3x to the 4th still. Okay, now what I want to do is I actually want to distribute this 2 to the infinite sum. And if I do that, I'm going to get the limit as x approaches 0 of x squared minus 2 plus 2 minus, so x squared over 2 factorial times 2 is just x squared. And then I will write 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial. I could simplify that by knowing what 4 factorial and 6 factorial are, but you'll see in a second that it's not necessary that I simplify that. Okay, so what you might notice here is what happened is that we have a lot of terms that cancel out. I guess I should write the denominator. Let me do that. So the denominator is 3x to the 4th. Yeah, like I was saying, a lot of terms cancel out. We have an x squared and a minus x squared. We have a minus 2 and a positive 2. And so what we're left with is just this infinite sum over here. So let's just write down the simplified version. This is the limit as x approaches 0 of 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus blah 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 divided by 3x to the 4th. Well, now what we can do is we can notice that there's an x to the 4th in everything. And so we could factor out that x to the 4th on top. I'm actually running out of space on this slide, so let me try and write it to the right here. We're going to factor out an x to the 4th on top. We get 2 over 4 factorial minus 2x squared over 6 factorial. This continues on indefinitely. Divided by 3x to the 4th. And now we can cancel out the x to the fourths. All right, so at this point, this limit looks like this. It is the limit as x approaches 0 of 2 over 4 factorial, and then there's also a 3 in the denominator, minus 2x squared over 6 factorial times 3 plus dot dot dot. And the idea is that every term in the dot 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 after this guy has an x in it. And since we're taking the limit as x approaches 0, this whole thing is just 0. And every term after it is also 0. And so all we are left with is just 2 over 4 factorial times 3. And if we actually calculate that out, we get 1 over 36. So in this particular example, from the beginning, if I just gave you this limit and didn't tell you how to evaluate it, I think it actually probably would have been easier to use L'Hopital's rule, however many times it was necessary. And that probably would have been an easier calculation. But it's not always the case. Sometimes using a Taylor series expansion actually is the way to solve a problem like this. And so this is another tool in our toolbox to solve certain types of limits. Remember that we have to pay attention, special attention, to what this limit is approaching. And we have to replace the function with the Taylor series expansion around that number. So if this was the limit as x approaches 5, we would have to consider the Taylor series expansion of cosine of x centered around 5. And you would have to calculate that by hand in order to shove it into the limit. And so, yeah, that's how you would go about doing a problem like this. Let's now talk about another application. Let's talk about differentiating power series. So we can also take derivatives of Taylor series to develop new types of Taylor series, much like what we did in section 11.2. So here's a quick example. We are going to show that the derivative of sine of x is equal to cosine of x using their Maclaurin series. So let me remind you first of all what sine of x is equal to. Let me actually use the thicker marker. Sine of x is equal to the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k plus 1 divided by 2k plus 1 factorial. It looks very similar to the cosine function, except instead of 2k, we have 2k plus 1. All right, so the derivative of sine of x, d by dx of sine of x, is equal to the derivative of its associated Maclaurin series. So we just replace sine of x with its Maclaurin series. Okay, so the key fact that I'm about to utilize is the fact that the derivative of a sum of terms is the sum of the derivative of terms. So like just how we know that the derivative of x squared plus cosine of x is equal to the derivative of x squared plus the derivative of cosine of x, we're going to make the derivative apply to each individual term. All right, so we can basically swap the derivative and the summation. And so I can write this as the sum from k equals 0 to infinity of the derivative of this entire thing, negative 1 to the k, x to the 2k plus 1, divided by 2k plus 1 factorial. Further, I notice that the only term that has an x in it is this guy. And so that's really the only thing that I'm going to differentiate here. So I can rewrite this sum once again as negative 1 to the k divided by 2k plus 1 factorial times the derivative of x to the 2k plus 1. And I am now going to take the derivative of that term. Well, the derivative of x to the 2k plus 1, that's just some power of x, so we reduce it by 1. So we're going to bring the power out front and reduce that power by 1. So we have 2k plus 1 times x to the 2k, 1 less power. And we can simplify this. Notice, if I can squeeze it here on the bottom, we have a 2k plus 1 and a 2k plus 1 factorial. Those cancel out a little bit and leave me with just 2k factorial on bottom. And so I can rewrite this as negative 1 to the k over 2k factorial times x to the 2k. And what do you know? This thing is exactly cosine of x. And so this is one way to show that the derivative of sine of x is equal to cosine of x. If you wanted to avoid the delta epsilon proofs that we did back in Calculus 1, you could instead choose to use the Taylor expansion of sine of x and cosine of x to verify that this is indeed true. So this is an alternative proof. So this is kind of neat. Note that this also works for any value of x because the interval of convergence for sine of x and cosine of x was negative infinity to positive infinity. And so this should be true for all values of x. Okay, so that's another thing we can do. The key thing to notice on a problem like this is that this derivative can be moved inside the sum, and it will only apply to things that have x's in them. Everything else is treated as a constant. This negative 1 to the k is a constant. This 2k plus 1 factorial, that's a constant, at least with respect to x. And so we can move it outside of the derivative. All right, let's continue. The next thing we're going to do is we're going to give you your first formal introduction to differential equations. So many of you in this class are engineers, and as engineers, you are going to most likely have to take the class on differential equations. So I'm a bit disappointed that this is the first introduction that you get to it. It's a very important concept that you will learn about in much more detail later on. But the basic concept that we want to get across to you here is that Taylor series can be useful whenever you are analyzing differential equations. And so here is one way that you can use differential equations. So first, let me just explain what a differential equation is. Differential equation is an equation involving derivatives, where you solve for a function. You can use Taylor series to give some insight into the problem that we're solving. So, for example, we are asked to find the power series solution of the differential equation f prime of x equals f of x plus 2. where we're given the initial condition that f of 0 is equal to 6. The thing that we are solving for is not a number. We're not solving for x or anything like that. We're solving for an equation. We're trying to figure out what f of x is equal to as some sort of function. So we claim that f of x is like cosine of x, or x squared plus 5, or natural log of x, or something like that. And we're trying to figure out specifically what that function is. All right, so one thing that we can do is to just take this differential equation and derive it a bunch of times. And then we're going to plug in 0. So let's give that a shot. So let me actually just write it down. The strategy. Derive the differential equation multiple times. And then plug in 0. The reason we're plugging in 0 is because we were given some information about what happens at f of 0. We were told that f of 0 is equal to 6, and we will use that information later. So let me perhaps make it clear where that 0 comes from. It is because of that. Whatever your initial value is, you're going to plug that in later on. All right, so we know that f prime of x is equal to f of x plus 2. Let's just take the derivative of both sides. So the derivative of the left-hand side is f double prime of x, of course. The derivative of the right-hand side is f prime of x. And this constant 2, whenever you take its derivative, just goes to 0, so we're just left with f prime of x. All right, and then we also know that f triple prime of x, so if we take the derivative again, we get f triple prime of x equals f double prime of x. And then we can continue. F 4 derivatives of x is equal to f 3 derivatives of x. And for each of these, we are going to plug in 0. So if we plug in 0, we get f prime of 0 equals f of 0 plus 2. Here, f double prime of 0 equals f prime of 0. F triple prime of 0 equals f double prime of 0. 4 derivatives of f, evaluated as 0, is also f triple prime of 0. And then if we actually look at this first equation here, we know what f of 0 is. We don't know what f prime of 0, or f double prime, or f triple prime, or f quadruple prime is. But we do know what f of 0 is. We know that it's equal to 6. And so let's just plug it in. We have that that's equal to 6 plus 2, which of course is just 8. So now we know that f prime of 0 is equal to 8. Let's use that information here. If f prime of 0 is equal to 8, then f double prime of 0 must be equal to 8. And f triple prime of 0 must be equal to 8, because now f double prime is equal to 8. And so on and so forth. These are all equal to 8. Okay, so the takeaway here is that every derivative evaluated at 0 is equal to 8. So f prime of 0 equals 8, f double prime of 0 equals 8, f triple prime, f quadruple prime, all equal to 8. Now, let's consider the Maclaurin series for f of x. The Maclaurin series is f of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 divided by 3 factorial times x cubed, and so on and so forth. We know what these values are now. We know that f of 0 is equal to 6, f prime of 0 is equal to 8, f double prime is equal to 8, f triple prime is equal to 8, and so we're just going to plug those in. So we can write that this is equal to 6 plus 8x plus 8 over 2 factorial x squared plus 8 over 3 factorial x cubed, so on and so forth. We could rewrite 6 as just 8 minus 2. All right, and so let's actually instead write it as negative 2 plus 8. So we have negative 2 plus 8 plus 8x plus 8 over 2 factorial x squared plus 8 over 3 factorial x cubed, so on and so forth. And so now let's factor out an 8 from all of the terms that have an 8. So we can write it as 8 times 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus blah, blah, blah. And what you might notice at this point is that this infinite sum is the Taylor series expansion for e to the x. So let's write this as an infinite sum. This is sum from k equals 0 to infinity of x to the k over k factorial. And so this is negative 2 plus 8 infinite sum and that infinite sum, as I've already said, is e to the x. And perhaps I should write that down, because the sum from k equals 0 to infinity of x to the k over k factorial equals e to the x. So it's Maclaurin Series expansion. And so what have we done? We have shown conclusively that the function f of x is equal to negative 2 plus 8 e to the x. So we now have a way of writing f of x without using a derivative. We don't have to write that f of x is equal to f prime of x minus 2. Instead, f of x is just equal to negative 2 plus 8 e to the x. So this is your first introduction to differential equations. It almost certainly will not be your last. So make sure you get comfortable with it, because you will certainly see these things again. They're very useful in engineering applications. All right, let's do another example. This is a different application. We're now going to approximate a definite integral. So we are going to approximate the value of this integral with an error no greater than 5 times 10 to the negative 4th. So first of all, note that this integral is one that cannot be solved with the techniques that we have so far. There is no u substitution that works really nicely. Integration by parts is not going to work. There's not really a whole lot else you can think to try. It's not a trig integral. It's not one where trig substitution presents itself nicely. And so we kind of just have to approximate this integral. Moreover, this is a very important integral in use for things like statistics. And so if you ever go into a class with statistics, you may encounter an integral of this form. All right, so anyway, we want to approximate this integral with an error no greater than 5 times 10 to the negative fourth. So where do we start? Well, we're in the section about Taylor series, so let's consider some Taylor series here. We know the Taylor series expansion for e to the x is, as we just discussed in the last problem, the sum from k equals 0 to infinity of x to the k over k factorial. So then, we can also come up with the Taylor series expansion for e to the negative x squared. And this idea is one that we talked about in a previous section. Basically, the only thing we have to do is replace the x with negative x squared, because this is a power of our x, and we multiply by a constant. All right, so we can write this as negative x squared to the k power divided by k factorial. All right, and we can simplify that. We can write this as the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k all over k factorial. The basic idea is just that negative x squared to the k can be rewritten as negative 1 times x squared all raised to the k, and then you can take each piece separately. So negative 1 to the k times x to the 2k. All right, so let's use this information. We then can write that the integral from 0 to 1 of e to the negative x squared dx is equal to the integral. We're going to replace e to the negative x squared with its Maclaurin series expansion. And so this is going to be the sum from k equals 0 to infinity of negative 1 to the k x to the 2k all over k factorial. And then there's still a dx here. All right. Just like we did with, I should have 0 and 1 as my bounds. Just like we did with one of these previous examples where we split up the derivative term by term. Notice how the derivative can be split by term whenever you sum a bunch together. We will do the same thing here, except we are going to split the integration term by term. So we can swap this integral with the summation. And so that's going to look like the sum from k equals 0 to infinity of an integral from 0 to 1 of negative 1 to the k x to the 2k all over k factorial dx. All right, the next thing to notice is that the terms here, negative 1 to the k over k factorial, those are both constants with respect to x. There are no x's in them, so we can bring them outside of the integral. And so that's going to look like the sum from k equals 0 to infinity of negative 1 to the k over k factorial of the integral from 0 to 1 of x to the 2k dx. Next, we need to consider evaluating this integral. All right, so x to the 2k, well, 2k is just a number, so if we increase the power by 1 and then divide by the new power, we're going to end up with the sum from k equals 0 to infinity, negative 1 to the k over k factorial times x to the 2k plus 1 divided by 2k plus 1 evaluated from 0 to 1. Okay, let me make this a little clearer. All right, and we are going to now plug in this 0 and 1 for x. So be careful, the variable that we were integrating with respect to was x, not k. So we're going to plug in 1 in for x, and then 0 in for x, and see what happens. So this is the sum from k equals 0 to infinity of negative 1 to the k over k factorial times, if we plug in 1, we would get 1 to the 2k plus 1 over 2k plus 1 minus, and if we plug in 0, we would get 0 to the 2k plus 1 divided by 2k plus 1. Well, of course, 0 to the 2k plus 1 is just 0, so this whole term is just 0. And then 1 to the 2k plus 1 is just 1. And so what we are left with, I think I'm going to have to move everything up just a slight bit, is the sum from k equals 0 to infinity of negative 1 to the k over k factorial times 1 over 2k plus 1. All right, so that's our start. We have computed the integral, but this isn't quite what the question was asking for. It was wanting us to approximate the value of this integral with an error no greater than 5 times 10 to the negative fourth. So how do we approximate an error? Well, there are 3 different types of errors that we have come across so far whenever we have infinite series. The first one was whenever we were looking at series using the integral test. And so the idea with that one was that you could, if your infinite sum was positive, decreasing, and continuous for all values of k, then you could consider using that error approximation. Unfortunately, we can't integrate this at all because we don't know how to integrate k factorial. Moreover, it's not positive for all terms because we have this negative 1 to the k, so that test is out the window. The second thing that we talked about was the alternating series error estimation test. And you'll notice that this is indeed an alternating series. Since it is an alternating series, we should recall the alternating series error estimation from section 10.5. So let me do that here on the next slide. The alternating series error estimation, alt series error estimation, had the following theorem. We know that, first of all, let's define AK to be everything except that negative 1 to the k. So it's going to be 1 over k factorial times 2k plus 1. Okay. So the error estimation says that the absolute value of the remainder is less than or equal to, can you guys help me fill in that blank? Can you tell me what goes in that next slot? The answer is that this is less than or equal to an plus 1, the first omitted term of the partial sum. And for us, an plus 1 is 1 over n plus 1 factorial times 2 times n plus 1 plus 1, which that is equal to 1 over n plus 1 factorial times 2n plus 3. Right? And the key concept that we learned from the alternating series error estimation is that we should set, let's see, so now set this value to be less than or equal to our error, 5 times 10 to the negative fourth. Okay, and in section 10.5, whenever we were doing this, what we often did was we set this up, and then we attempted to solve for n. So in the previous section, we would have something like 1 over n squared is less than, let's say, 10 to the negative sixth, and then we would have to solve this for n, and you would get like n is greater than, let's see, that would be 10 to the third, something like that. But unfortunately, this problem, it's basically impossible to solve explicitly for n. So we can't solve this explicitly for n. So the alternative here is just to guess and check. We are going to try a bunch of different values for n and see if they produce a value that is less than 10 to the negative fourth. Okay. The idea, let's use this chart here. If we plug in 1 into this thing, then what we will end up with is a value of 0.1. So just for instance, we would have 1 over 2 factorial plus, 1 over 2 factorial times 5. And if we multiply that out, we would actually end up with just 1/10, which is 0.1. If we were to throw in 2, and notice that 0.1 is not less than 5 times 10 to the negative fourth. So no, it is not less than 5 times 10 to the negative fourth. If we plug in 2, then we would get 1 over 2 factorial, 2 factorial times 7. And that number is approximately 0.02, which once again is not less than 5 times 10 to the negative fourth. Same thing if we plug in 3. We would get 0.0046, so the error is getting smaller, but it's still not quite as small as we want it. If we plug in 4, it's still not smaller than what we want. It is just barely larger than 5 times 10 to the negative fourth. And if we were to plug in 5, finally, we get that it is indeed, let me use a different green, it is indeed smaller than 5 times 10 to the negative fourth. So we do get what we are looking for. So the conclusion that we can reach here is that realize that we need more than 5 terms, at least 5 terms are required to ensure that the error in estimating the integral of e to the negative x squared dx with its Taylor series expansion is that required to ensure that the error in estimating that integral of its Taylor series expansion is less than 10, or it's less than 5 times 10 to the negative fourth. All right, and the actual answer that we come up with whenever we use 5 terms of the Taylor series expansion is that this integral of e to the negative x squared dx is approximately equal to 0.747. And this number, 0.747, comes from this Taylor series whenever we use the first 5 terms. So if I were to just consider the sum from k equals 0 to k equals 4, that's the first 5 terms, then that would give me this number. All right, and I can guarantee that this is within 5 times 10 to the negative fourth of the true answer. All right. So this is a very useful technique, but there was definitely a lot that went on in this problem. We had to first write out the integral of e to the negative x squared. We had to notice that e to the negative x squared could be represented by this Taylor series. We had to actually do the integration. And let's just take a moment to appreciate something that looks like this. Like if I would have told you that we were working with this at the beginning of the semester, and you would be able to solve it, I think you would have your eyes glaze over because this just looks impossible. You've got an infinite sum, you've got an integral, you've got k's, you've got x's, but nevertheless it's manageable and it's something that we can do. So you guys have made some incredible strides in this class, and so you should pat yourself on the back for it. So yeah, we would end up getting this sort of infinite sum. And then we had to notice that this was an alternating series, so we could use the alternating series error estimation technique. We had to use guess and check to eventually figure out that 5 terms were necessary to get an error that was less than 5 times 10 to the negative fourth. So a very involved problem, lots of steps, lots of places to go wrong. So yeah, if you have any questions about this example or any others, please just let me know and I'm happy to work through them with you. The next example, the next thing that we're going to be using Taylor series for, is representing real numbers. So if we're given the prompt to find the exact value of this infinite sum, you might look at me and say I'm crazy because we don't know how to do that. What I have told you so far is that there are only 2 types of series for which you're able to calculate exact values. That was a geometric series, where we could write that the infinite sum was a over 1 minus r, if the absolute value of r was less than 1. And the second one was a telescoping series, a very limited value type of series, where you had to calculate the partial sum Sn, and then you would take the limit as n goes to infinity of that thing. So up to this point, these are the only 2 types of series for which we know how to exactly evaluate series. But what I'm telling you now is that there is another clever technique that we can use to calculate exactly series like this. And the idea is to use Taylor and Maclaurin series in order to evaluate these. So the hint here is to consider the Maclaurin series for the inverse tangent of x. All right, so let me just write down what the Maclaurin series for the inverse tangent of x is. The inverse tangent of x, and this is one that we actually did, I believe, in section 11.1, 11.2, something like that. So if you're wanting to know where this comes from, go back and check those. It is the infinite sum from k equals 0 to infinity of negative 1 to the k times x to the 2k plus 1 over 2k plus 1. Okay. So I want you guys to notice the similarities between this series and this series. The only difference here is that this inverse tangent of x series includes this x to the 2k plus 1 term, whereas this one does not. So, what we can say is if this term was just 1, it would be exactly the same as this series. In other words, if we were to write the inverse tangent of 1, we replace x with 1, we would get just negative 1 to the k over 2k plus 1, because this entire term, x to the 2k plus 1, would just go away. And so, inverse tangent of 1, this thing, is equal to pi over 4, right? Because the angle that gives you a tangent of 1, tangent of what angle gives you 1, is pi over 4. And so, the concept here is that this infinite series is equal to pi over 4. Wow, that was easy. So, a lot easier than that last problem that we gave you. But the key trick here was noticing to use this series. And so, if we were to ask you a slightly different problem, so like, for example, estimate, let's say, a sum from k equals 0 to infinity of 1 over k factorial, what series would you use here? I want you to think about it. Maybe pause the video. The idea is that you would end up having to use the series for e to the x, because e to the x is equal to the sum from k equals 0 to infinity of x to the k over k factorial. And so this thing would just be e. So, yeah, the key trick is just kind of figuring out what this looks like. They could also change it up a little bit, and instead of saying 1 over k factorial, you could instead get something like, let me not change what I've written. Let me just do this thing. They could instead say like 2 to the k. And in this case, it would be e to the 2. All right, so the final example that I want to show you before I get to my little treat here at the end is writing functions as power series. So we want to identify the function that is represented by this power series and give its interval of convergence. The way that we're going to do that is notice what this kind of looks like. And in this case, this once again looks very similar to the e to the x Maclaurin series. So let me rewrite the Maclaurin series for e to the x. It is the sum from k equals 0 to infinity of x to the k over k factorial. And this is true for x within negative infinity to positive infinity. In other words, I, the interval of convergence, is negative infinity to positive infinity. So we can write that e to the 1 minus 2x is equal to the sum from k equals 0 to infinity of 1 minus 2x to the k. All we did was replace this x with 1 minus 2x. All right? And so now the idea is, how does this change the interval of convergence? Well, if originally we had that, let me rewrite this like this. Originally we had x between negative infinity and positive infinity. Let's replace that once again with 1 minus 2x. This occurs if and only if, so we're going to subtract 1 from every side. That doesn't change the negative infinity or the positive infinity. And then we're going to divide every side by negative 2. That will actually change negative infinity into a positive infinity, and it will flip the inequality, right? Because if we divide by a negative number, that flips the inequality. And then it will change the positive infinity into a negative infinity. And so this essentially is just the same thing. The interval of convergence is still negative infinity to positive infinity. And once again, this isn't too difficult of a problem. It's just observing what this series looks like. And it indeed looks similar to the e to the x series. And so the main concept here is now we can write this function, e to the 1 minus 2x, as a power series, as a Maclaurin series. And so we now have this thing. All right, so the next result that I'm going to show you guys is my favorite result in all of mathematics. This thing that I'm about to show you is going to be, no joke, what I print on my gravestone. So let me blow your mind, and I think this is kind of what you've all been waiting for. It's the culmination of mathematics. All right, so what we're going to do is we're going to prove Eulers' identity. So Leonhard Euler is one of the most famous mathematicians in all of history. He is responsible for thousands of important results, which are still used today. The number e is literally named Euler's number. That's why it's e. And Euler went blind near the end of his life, but still wrote about one mathematical paper every week, which is absolutely insane. People that are alive today are lucky to get mathematical papers published once a year. So that is truly a remarkable feat. Today, we're going to prove one of the most profound mathematical statements ever, and that is Euler's identity. And so, the first thing we're going to do is we're going to start by recalling the Maclaurin series for e to the x, cosine of x, and sine of x. The Maclaurin series for e to the x is the sum from k equals 0 to infinity of x to the k over k factorial. We can write this as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. I think I'm actually going to give myself a little bit more space. Plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial, and this goes on and on. All right, the Maclaurin series expansion for sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then this goes on and on. And you'll see why I spaced it out like this in just a second. The Maclaurin series expansion for cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. It's just the even powers of x, whereas sine is all the odd powers of x. And what you might notice is there's some sort of relationship here between e to the x and sine and cosine. Specifically, it looks like these terms kind of line up. There is a little bit of a discrepancy here. Notice that we have negatives for some of these terms and positives up here in e to the x. So let's see if we can find a way to relate these three functions together. One thing that we know is that the number I, remember that is the imaginary thing. It is defined to be the square root of -1. We know that I squared is equal to -1, and I cubed is equal to -I, and I to the 4th is equal to +1, and then it repeats this process. So I to the 5th would be I to the 6th would be -1, I to the 7th would be -I, and I to the 8th would be 1. So we can actually use this idea to consider e to the ix. So e to the ix, a very strange thing to consider, is the sum from k equals 0 to infinity of ix to the k power over k factorial. So remember that e to the x is just the sum from k equals 0 to infinity of x to the k over k factorial. So if we replace x with ix, then it's not that far of a leap to believe that this is just ix raised to the k power. It is a little bit weird that we're putting in an imaginary unit there, but we'll just run with it. So if we expand this out, we would get 1 plus, so actually let's look back here. Every time we see an x, we're going to replace it with ix. So 1 plus ix plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus I to the 4th x to the 4th over 4 factorial plus I to the 5th x to the 5th over 5 factorial. And I'm going to once again have to give myself a little bit of space. Plus I to the 6th x to the 6th over 6 factorial, and this continues on and on. Let me make this look a little bit cleaner. Okay. All right, so now let's replace all of these i's with what they're supposed to be. So I is just I. I squared is -1. So instead of a plus here, let's write this as a minus. This is minus x squared over 2 factorial. I cubed is just -I. And so we can write this as minus I x cubed over 3 factorial. Let me actually put that I out front. I think that'll make things a little bit nicer. I to the 4th is just 1, so that's nice. We can just write this as x to the 4th over 4 factorial. I to the 5th is I, and so we can write this as I x to the 5th over 5 factorial. X to the 6th, or I to the 6th rather, is -I, and so we can write this as -I x to the 6th over 6 factorial, and once again that continues on indefinitely. We can further simplify this. Let's actually consider what happens whenever we factor out all the terms that have an I and all the ones that don't have an I. So let's write this as, first of all, let's consider all the terms that don't have an I. So that would mean this guy, this guy, this guy. Did I mess up somewhere? Oh, yeah, there should not be an I over here on the x to the 6th. That's because I squared is just negative 1, not negative I. That's my mistake. Yeah. And this guy. So we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And that continues on forever. And then let's consider all the terms that do have an I. So that's this guy, and this guy, and this guy. So plus, I'm going to put this I on the outside. I'll factor it out of all of them. We're going to have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... And what you might notice at this point is that this thing in blue is exactly cosine of x. That is precisely the definition of cosine of x. It is all the even powers of x, and it alternates like it should. Also, what you might notice is that over here in orange, this is exactly sine of x. And so what we have, remarkably, is that e to the ix is equal to cosine of x plus I sine of x. This is already pretty astounding that we can relate e to the ix to a cosine of x and a sine of x function. This function is actually used all the time in physics. It's very useful. And it's one of the cool applications of using the imaginary unit I. But this becomes even more astonishing whenever we consider what happens whenever you plug in x equals pi, right? So consider plugging in x equals pi. We get that e to the I pi power is equal to, well, cosine of pi, that is negative 1, and sine of pi is just 0, and so this whole term just disappears. So let's just erase that. And what we are left with is this absolutely amazing identity that e to the I pi power is equal to negative 1. And this is Eulers' identity. And let's just take a second to appreciate how astonishing this is. We have e, which is a number that is used whenever you're defining compound interest, right? Maybe that's the first application that you heard of it. It was the number also that when you raise it to the x power and you take the derivative of it, you get exactly itself. The derivative of e to the x is e to the x. You know, it's just this amazing number that appears in a variety of applications. It's a very strange number, or 2.7 approximately. We have I, which is just defined for engineers for convenience whenever you have quadratics that don't work out very nicely and they have imaginary roots. We define it to be the square root of negative 1, which no one ever thought would be useful, right? Whenever you learn this in Algebra 2, I'm sure this just seemed like a foreign concept. You would never use this. You have pi, which is used for circles. It is the ratio of a circle's circumference to its diameter. And the combination of these three numbers together gives you just a very simple negative 1 on the right-hand side. And I don't need to tell you why 1 is important. Like, 1 obviously is one of the most crucial numbers in all of history. And the fact that this is true is just ridiculous. We can even make this look a little bit nicer, and sometimes people write it like this. If you add 1 to both sides, you could write this as e to the I pi plus 1 equals 0. And then this is also considered Eulers' identity. And so now you start to involve 1 and 0, which are both crucially important to all of mathematics. And so you get this remarkably beautiful formula that relates all of these disparate numbers but very important concepts in mathematics all together in a way that we never would have expected. Like if I would have told you at the beginning of this lesson, calculate e to the I pi power, you would have told me I was insane. And so this is, in my opinion, remarkably beautiful and shows some sort of connectedness to the universe that I don't quite get. And if you don't think this is beautiful, then as my friend at Khan Academy says, you have no soul. So I hope you enjoyed that as much as I did. This is all I have for you from chapter 11. And in chapter 12, we're going to be discussing something about parametric equations. And so I hope you join me back there for that. Until then, I bid you adieu. Have a great night.